But today we have Dan Boneh, who will tell us about computing aggregate statistics privately. And how would you like students to ask questions?
Oh, I think it's best if people just interrupt, just jump right in and ask a question. I can't really see the chat here, so if anybody has a question, just jump right in. Great. Okay,
Sure.
so yeah, should we get started?
Yep.
Okay, terrific. So indeed, today I'm going to tell you about how to compute aggregate statistics privately. Yeah. So this is actually work that's been something we've been working on for quite a while. I'm going to tell you about some recent results that we have, and I think it's really elegant math that's involved here, and maybe I can get you interested in kind of thinking about these questions for yourself. Okay, so let's jump right in. So I guess this talk comes in two halves. Yeah, the first half is going to be kind of an overview, just motivating the problem, and then the second half will be much more math. Okay, mathy. So let's jump right in. So right. So the problem is, imagine you have a company that wants to collect information from users. Yeah. So here we have like an example of a company maybe that runs a web browser. Yeah. So think of any company that makes a web browser, and maybe they want to know which URLs happen to crash the browser. Yeah, so maybe they have like a list of like 100 URLs, and they suspect that one of these 100 URLs, when somebody visits that URL, the browser crashes. Yeah, and they want to know basically how many people actually visited that URL and the browser crashed. Yeah, so here you can see user number 1 visited URL number 2 and the browser crashed. Visited URL number 3 and the browser crashed. User number 2, that means that's what this 1 means. User number 2, you can see visited URL number 1 crashed, visited URL number 3 crashed, and all the other ones didn't crash, and so on and so forth for all the remaining users. Yeah, so you can think of this as every user has basically a vector that indicates whether the browser crashed at that URL or not, and so it's kind of a binary vector that the user actually has. Now, what the company is interested in is basically sort of the sum of all these vectors, right? So it'll tell it that, oh my God, URL number 3, a lot of people that come to visit this URL, the browser crashes at this URL, so they have to go figure out what's going on here and fix the browser. Okay, so they're interested in the sum of all the vectors, but you realize, of course, these vectors are very private, right? They kind of tell the company which websites you've been to. So generally, it's kind of a bad idea to send this data over to the web server, because then the web server will know everything that you've done with your browser. Yeah. And by the way, I should say actually, this is not just about URLs and browsers. I want you to think about this is a very general problem. So for example, maybe we have a list of 100 restaurants and we want to know what are the popular restaurants, where are people eating. You can imagine every user in the system would have a binary vector saying, this week I ate at the following 3 restaurants, and what the company is interested in the sum of these vectors, and that will tell it what are the most popular restaurants in the town. Yeah, or you can imagine maybe how many people use a particular feature of their car, how many people use a particular feature of their fridge. Basically, there are a lot of companies that are interested in basically how consumers use products, but they're interested in just sort of aggregate behavior. They're not interested in specifically how you yourself use the product. Unfortunately, so we have these vectors, and the goal is to kind of compute the sum of these vectors. Unfortunately, the way this is typically done today is everybody sends their vector over to the server. The server sums up the vector, and you end up with the total sum, which is what the server wanted to. Unfortunately, what this means is, even though the server only wanted the statistics, it only wanted to know the sum, it didn't want to know anybody's individual data. In this case, it actually learns everybody's data. Yeah, so it doesn't just learn that you visited this URL. It doesn't just learn that 3 people visited URL number 3. It learns exactly which 3 people visited URL number 3, and that's not something it wants. Yeah, or in the case of restaurants. Oh yeah, there's a question.
Yeah. So, and by the way, couldn't you just kind of like delete that data from the server and just put in the total?
Oh, you could. So the server could actually collect all the vectors, compute the sum, and then delete all the vectors, right? That's, I think, what you're suggesting. But how do you know that the server actually did that, right? You have no guarantee that the server actually deleted the vectors, or maybe an attacker already compromised the server, and now the attacker got to see all the vectors in the clear. So there are lots. It's a very good question.
Oh,
but that's kind of
so
unsatisfying.
the server is out of your control.
Yeah, exactly. You'd like to kind of you'd like the server to just learn the sum, but not learn anything about the underlying data. Yeah, we'd like, they need to see statistics about what people are doing, but they shouldn't know about what any particular person is doing. Okay, so there's a kind of a natural way to do this, and that's what's called private aggregation using secret sharing. And let me just say this at a high level, and I'll explain in just a second how it actually works. But basically what we're going to do is we're going to introduce a second server. Yeah, so we're going to have our main server and our second server. And the assumption is that these servers actually don't collude with one another. Yeah, they're kind of independent servers. Now, what user number one will do is it somehow, in a way that I'll show you in just a second, it's going to take its data and it's going to break it into two shares. Yeah, and it's going to send one share to one server and one share to the other server. And again, I'll show you how that's done in just a second. The second user will do the same thing. The third user will do the same thing, and so on and so forth, right? So now, basically, the first server basically just has a bunch of shares. That doesn't tell it anything. It just sees kind of random data. The helper server also has a bunch of shares. It doesn't tell it anything. It just sees a bunch of random data. But now, once they've finished collecting all the data, what they'll do together is maybe they'll talk to one another very briefly. And again, we'll see how in just a second. And now all of a sudden, the sum will appear, even though they didn't learn anything about the underlying data. So they don't learn any user data, but the sum just becomes available to them. So again, the point is only the final result is revealed. And the underlying data, my particular data, your particular data is never exposed to the servers.
Basically, like it has like by random data, you mean, okay, sum along user one, like
yeah, I'm going to show you how this works in just a second. Yeah, we'll see exactly how this works in a second. Actually, in fact, let's see exactly how this works. So I'm going to describe this actually very, very concretely. And so let's basically say where the data comes from. So let's fix what's called a prime finite field. If you don't want to know what a prime finite field is, it's not that important. Basically, think of this as choosing a prime. Yeah, so we'll choose some large prime, and we're basically doing arithmetic modulo that prime. So addition, subtraction, multiplication, all is happening modulo this prime. And basically the numbers 0, 1, 2, 3, up to p minus 1, that's what we call the finite field. That's our set F, okay? Now, every user basically has a vector, right? Every user has a vector of elements over this field. So we'll say the vector has length n, and it's a vector of elements over this field. Yeah. So again, this would say like for URL number 1, maybe the user visited the URL or didn't visit the URL. So the first element of D1 would either be 0 or 1. The second element of D1 would similarly be 0 or 1. How do we share the data? Well, what does secret sharing actually mean? What the user will do is it's going to choose a completely random vector, completely independent of its data, just completely random vector, and send that over to the helper. Now it's going to send its data minus the random vector over to the first server. So you notice the helper just sees complete random junk. The main server, it sees the difference of random junk and the actual data, and it's actually not that difficult to show that D1 minus R1 actually is a truly random vector. So by itself, this vector D1 minus R1 doesn't reveal what D1 is. Maybe you guys have heard of something called a one-time pad, which is a way to encrypt information. Effectively, what's happening here is R1 is like a secret key that's used to encrypt D1 using the one-time pad. Yeah, basically, the subtraction reveals no information about D1. So you notice what's interesting is neither one of these servers learns anything about the data. Of course, if they get together, they can sum up the two shares, and then they'll see the data in the clear. But by themselves, they don't learn anything about the data. Oh, I see that somebody has a question. Utsav, you want to ask a question?
Yeah, wait, why do we have to do this? Why can't they like send just the URL every time a crash happens, which doesn't have the user data? Because then they're just variables in the server that doesn't destroy anything from the user. I feel like this one could also be hacked if someone just gets access to both the servers and puts it together.
Yeah, so the assumption is that the servers don't collude, yeah, so that you can't actually get the two elements together. And if you just send the data to the server directly, the server will know that it's your data, and we're trying to avoid that. Yeah.
Oh, you mean like
So-
server logs and stuff here?
Exactly.
I see, I
Yeah.
see.
You see, with this, even if the app server, this guy up here, even if he logs all the data, it doesn't help him, because all he will see is just completely random data. Yeah, it just sees a random vector. So this basically he can log as much as he wants here. It's not going to help. He just sees random data. Oh, I see this. Sriram also has his hands up. Sriram, you want to ask your question?
Yeah, can you re-explain this prime finite field concept? I don't really get how that ties into this.
Oh, this is just a way to represent data. Yeah, so we need a way to represent numbers, and in particular, we need a way to subtract one vector from another. So when I write subtraction here, what I mean is subtraction modulo p. Yeah, so I hope you know how to do addition, subtraction, and multiplication modulo a prime. Yeah, so the elements in the finite field are just the numbers 0, 1, 2, 3 up to p minus 1. Yeah. So there are 2 to the 6, there are p elements in this finite field, 0, 1, 2, 3 up to p minus 1. And when I write subtraction here, what I mean is just subtract one vector from another modulo this prime p. Yeah, does that make sense?
Yeah.
And the reason we need this, the reason we need to work modulo a prime is because when you work modulo a prime, you can show that this subtraction reveals no information about the data. Yeah, if we were using integers, then this subtraction would actually reveal information about D1. This wouldn't, R1 would not be hiding D1. So the reason we need to work mod prime is to make sure that R1 completely hides all the data in D1. So the app server basically sees nothing.
I have
lots of questions. Yes,
another
Sriram.
question.
Just a minute. I see that Sriram has his hands up. So please go ahead and ask your question.
No, that was from a previous question. I just lowered it.
Oh, I see. Okay. Sounds good. I don't see the chat, so you're free to kind of either raise your hand or just ask your question right away. Dallas, you can ask your question.
So so first of all, I have two questions. One, so why do we need, but if D1 is either just 0 or 1, shouldn't F be the field, shouldn't the prime P be 2, because it's just integers modulo 2, because that is 0 or 1?
Yeah, so you'll see why we want it to be larger than 2 in just a minute, but maybe just to look ahead. Remember, we're trying to figure out the sum of all of these.
Because
right?
it's not 0 or 1 mod 2, it's 0 1. D1 is 0 or 1 mod P.
Mod P, exactly.
So I mean D1 is actually a bit limited here, but it's fine. And then so if it's just the integers, maybe D1 minus R1, are you saying that would reveal information? Well, yeah, why would it reveal information if it's modulo a composite or just the integer?
You know, actually, maybe that's something that we can discuss later because we have a lot to cover. So just trust me that the way to do this is to do this subtraction modulo a prime. This is the way to hide information. Yeah, maybe you can think yourself a little bit like if you did this over the integers, there's information revealed about D1. Okay, so the point is that neither one of these servers by themselves learn anything about the data. Okay, and we're going to do this, and every user is going to do the same thing, right? So we're going to go up to user number M, and the user M will do the same thing. They're going to split their data into these two halves, random half and a difference half, and they're going to send these values to the two servers. The nice thing about that is, as we say, each server is only going to see random data. They're not going to see anything that reveals anything about the data by themselves. Okay. So once this collection process is done, what do we have? We have that the one server has, these are called shares. You notice if I put brackets _L, these means left side of the shares. So one server has a bunch of left side shares from all the users. The other server has a bunch of right side shares from all the users. And all we know is if we add the left, for every user I, if we add the left share to the right share, we actually get the data for user number I. But as long as these servers don't collude by themselves, they can't reveal any, they don't learn any information about DI. Okay, so now they've collected all these shares by itself. This is useless to them because it's just random data. But now it turns out there's kind of a general cryptographic tool, which I'm not going to tell you much about. I'll just tell you there's something called a two-party computation that allows them to basically run an arbitrary analysis on this shared data. Yeah, so they can, if they want, they can compute a summation of all the vectors. If they want, they can compute standard deviation, they can compute averages, they can compute sort of whatever they want on the data from the users, but only learn the result of the analysis without learning anything about the underlying data. Yeah, so two-party computation is actually a pretty complicated topic, which I'm not going to describe here. What I wanted to do is just give you one example of something that they might want to derive. In particular, suppose they want to figure out the sum of all the vectors. Okay, so they want to figure out, as we saw, just the sum of the data from all the users. In particular, let's say that they want to sum all the users. Yeah, so the application wants the sum of all the user data that belongs to a particular set. Yeah, maybe this set corresponds to people in California. They're just interested in, what websites do people in California visit, what restaurants do people in California eat at, and so on. So they just want to sum over a subset of the data. What the app server will say to the helper, here's a subset of people that I'm interested in. What the helper will do, well, maybe you guys already see how to do it. What the helper will do is it will send back the sum of its shares of all the vectors that it got. Yeah, so it's just summing up the right shares of the data, and it'll get the sum H. And now what the app server can do is it will take H and add the left side of the shares. And you can see that taking the right side, the sum of the right side of the shares plus the sum of the left side of the shares actually gives us exactly the sum that we're interested in. Yeah. And so now the app server, by doing this simple summation, it gets to learn the data that it wants, but it learns nothing else about user data. Does that make sense? This is a very, very simple example where every user can take their data, they can break it up into two shares. Then when the app server wants to compute a sum over a subset of the shares, the helper can compute part of the sum, half the sum, and the app can compute the other half of the sum. And then if you add up these two halves, you actually get the sum that you're interested in. Does that make sense to everybody? If not, please ask, because I want to make sure this is clear. So this is an easy way to get the sum of all the data without actually learning anything about the underlying user data. Okay. In some sense, you could ask me, well, what is the helper doing here? It's kind of funny. The only thing the helper is doing is making sure that the set S is sufficiently large, right? In some sense, it will only answer queries if the set S contains enough users in it so that the app server actually can't just get information about one individual and nobody else, because that would reveal individual data. But aggregate information is okay to reveal. And so the helper server is really kind of making sure that the only thing the app server learns is just aggregate information. I saw that somebody had their hand up. So yeah, you can go ahead and ask your question. Suram, I think you had a question.
You just answered. I was going to ask, what if S is only size 1? But
yes, excellent. That's really, really good. Really, really good question. And yeah, the point is the helper would then refuse to answer the query. The helper is there just to make sure that the query is over a large enough set. Perfect. Okay, so you guys are with me. So you see how in this way, the app server will learn the sum that it wants, but it doesn't learn anything else about anybody's specific data.
And basically one thing that you're saying is so basically the app does learn H. So if we're working with the integers instead of just the integers modulo P, it's like, oh, well, H is the sum of these positive integers. So, maybe I know a little bit about
Yeah,
those.
we're not working over the integers. Integers would be insecure.
But why not modulo a composite number?
That will be fine too. But it's easier for us to work modulo primes, as you'll see in a minute. Yeah, good questions. I see Anuj has her hand up. Do you want to ask your question, Anuj?
Yeah. So basically, what's the limit needed for the helper variable to have a large enough size?
I'm sorry, but you were breaking up. I didn't hear.
What is the minimum limit?
That's a matter of policy. So, again, this is not something that I want to discuss here. The helper basically will have some lower bound of how many, what size sum it will compute, and otherwise it will not respond to the query. Yeah, and it's a matter of policy how big that set is.
How come it's easier to find the sum of the helper rather than the sum of the entire thing?
Well, the helper has all these values available to it directly, right, locally. So it can just sum up all the values that it has locally and send the result back to the app server. Right?
Okay.
Yep, that's it. And then the app server will compute the sum that it needs itself, add that to whatever the helper sent, and get the actual sum that it's interested in. Okay, very good. Any more questions on this? Please ask if something is not clear here. Okay.
Oh yeah.
So, yeah.
I guess like what I still don't fully get is why can't the app just do it itself?
Sorry, you don't get why what?
The app can't do it itself.
Well, if the app did it itself, well, first of all, in this setup, the app doesn't have the data. The app only has the shares of the data, and the shares of the data are just random vectors. So you can try to add the random vectors to themselves to each other, but you'll just end up with a random vector that's unrelated to the data. So it needs the helper in order to compute, both halves of the sum, so that the sum of the two halves gives it the sum that it's interested in, that it wants.
Where the helper is eliminated, then like wouldn't the app just have all the data as is?
Well, the whole point of the system is to make sure the app server doesn't actually see the data in the clear. So the app server will
Okay.
just see random data. It does not see any user data. Yeah. So you're
Right.
we're trying to let the app server compute the sum that it wants without seeing any private user data. And in this system, the app server will only see random data. It does not see any private user data. Yeah. So without seeing any private user data, it's able to compute the sum that it actually wants.
Okay, that's clear.
Okay, perfect. All right, sounds good. So let's continue. So unfortunately, there's a real problem here. Yeah, this sounds really good, but this doesn't work. And the reason it doesn't work is because imagine some user tries to be malicious. He wants to destroy this protocol. And instead of sending a vector of zeros and ones, it'll send some random vector. Yeah, some random large values. And as a result, this is some junk vector, basically. And as a result, when we compute the sum, we just get garbage. Yeah. So what this says, the problem basically is because nobody can see the data in the clear, nobody can verify that the data that the user sent actually is valid data, right? The users can just send arbitrary junk data and destroy the entire computation. And in fact, one malicious participant can destroy the entire study. Yeah. So
I understand that, but my question is, like, why? What? Wouldn't it still be a problem even if they send like a bunch of zeros and ones? Like, if they even if it's like it's still fake, wouldn't it still be a problem?
Well, if one user decides to send, bogus zeros and ones, they don't affect the sum by much, right? They change things a little bit only by a tiny amount. Here, one single malicious participant can destroy the entire study. Yeah. So that's the difference. That's what we're trying to avoid.
That's true. Yeah.
Okay, very cool. So the question is how to prevent this. Yeah, and this is kind of where this problem becomes interesting. So far, we just did some background. Now the question is how to prevent this. So what we'd like to do is basically we'd like to make sure that even though the servers, they don't see the data in the clear, somehow they should be able to verify that these vectors actually are valid vectors. For example, they're just 0, 1 vectors. Okay. And so the way we would do this is basically they would still send these shares. So they would send the left share and the right share to the two servers. But what they're going to do is they're going to attach what we call a proof to these shares. Okay, so there's a left proof and a right proof. And these proofs, pi L and pi R, they're just more data. What they'll do is they'll prove that DL plus DR, in fact, is a valid vector. So DL plus DR, for example, is a binary vector. Okay, that's our goal. Yeah, that's what we'd like to do. So they send these proofs pi L and pi R to the two servers. The two servers are going to do a very, very lightweight computation and then decide to accept or reject. If they accept, it better be the case that DL plus DR is a binary vector. And if they reject, then it should be that DL plus DR is not a binary vector. Yeah. So this is what's called this is kind of an odd looking, this is sometimes called a proof system, but it's a very strange situation for a proof system. First of all, let me tell you what the properties are. So it should be that if DL plus DR is really a binary vector, then the two servers should accept. This is what's called complete. The proof system should be complete. If the sender is honest, the vector should be accepted. Sound means that if the sender is dishonest, so DL plus DR is not a binary vector, then with very high probability, they should reject the server should reject the contribution from this user. That's what we call soundness, that a malicious user cannot fool the servers. The third property is something you may have heard of. This is what's called zero knowledge. I'm not going to define zero knowledge here. That actually takes quite a while. I want to focus more on the math. But zero knowledge would, at a high level, would mean that even after these servers run the computation, they learn nothing about DL plus DR. Yeah, so somehow checking that DL plus DR is a binary vector reveals nothing about DL plus DR other than the fact that it's a binary vector. So all they learn is that it's a binary vector, but they learn nothing about what DL plus DR is.
Which does sound hard. Like
Yeah.
like,
But in fact, it is indeed. Zero knowledge is a very interesting topic. This is something that if you want to hear about zero knowledge, is something that I'll have to come back to, because that's not what I'm going to talk about today. But in fact, it is possible to do. And of course, finally, we'd like this to be super fast. So these servers can actually support many users, even if they're very light servers. Oh, I see there are some hands up. So Soham, you want to ask your question?
Yeah, I was just wondering, like, how would, say, like a malicious user send like some data that isn't a binary vector? Like, how
Well,
would
so this is coming, for example, from your phone, or it's coming from your browser. In particular, you can kind of write a malicious application on your phone that what it does is it sends a random vector DL to the app server and a random vector DR to the helper server. So then DL plus DR is just some random junk, right? It's not the actual binary vectors. Yeah, it's not the actual binary vectors you're supposed to send. It's just DL and DR are both random. And so there's some will just be random junk, and that will destroy the entire summation computation. Yeah? Does that make sense? Oh, let's see. I see there are more hands up. Yeah, please go ahead. Sriram, did you have a question?
So is the helper machine something that is on the user's side, or?
No. The helper machine is not on the user side. The helper machine would be, you can think of like the app server would be like, I don't know, maybe it's some application developer on your phone, and the helper machine might be Apple. Yeah. So, Apple is promising not to collude with the application developer, but together they want to make sure that, this is an example, together they want to make sure that only valid inputs from users are accepted. Yeah, does that make sense?
Yeah.
Okay, cool. Any more questions? Please go ahead. Yeah, Anuj, I see you have a question.
But like, isn't the end goal to find out what DL plus DR is? So like, why can't it find
No,
out
heaven
that?
forbid. No, we don't want to reveal DL. DL plus DR is user one's data. We don't want to reveal DL plus DR. We want to reveal the sum of the user data over a large set.
Right, my bad. I confused them. Sorry about that.
Sorry, what? I didn't understand. Say it again.
My bad. I confused them. Sorry about that.
Oh, okay, good. No worries. No, it's good. I'm glad you're asking questions. It's actually tells me you're following along. Please, more of you should be asking questions. So are there any other questions? I'm very happy to answer. Okay, so let's continue. All right, so you see, so that's kind of our goal. Yeah, we'd like to, so these clients can provide these proofs, and then these guys, the servers will interact very lightly and check whether the data is in fact well formed or not, but they will learn nothing else other than the fact that the data is well formed. Good. So let me show you some examples of things we'd like to check. Yeah, so let's see. So again, the client has a data vector, D1 to Dn. The servers have shares, DL and DR, such that DL plus DR is equal to D. And some examples of things they would like to check is, they want to check that D is a Boolean value, right? So D is a vector of just zeros and ones. That's one thing that the two servers might want to check. Another thing the servers might want to check is that D is a unit vector. What is a unit vector? It means a unit vector is a vector that basically contains 1, 1, and everything else is 0. Yeah. So this would be an example if you have to vote for your favorite restaurant, right? So you're voting for your favorite restaurant. That's kind of the the one is your favorite restaurant, but you're only allowed to vote for one restaurant. And we're trying to compute the sum of all the votes so that we see what's the most popular restaurant in the town. Yeah, so the servers want to accept a unit vector but reject anything else. Another thing they might try to do is maybe they want to accept a vector that has up to k votes. Yeah, so every element in the vector is a number between 0 and k minus 1. And the sum of all the elements needs to be less than k. Yeah, that means that basically corresponds to the fact that you're allowed to vote for 5 restaurants, but no more than 5. You can vote for less, but no more than 5. And you're allowed to vote for the same restaurant twice if you wanted to. Yeah, that's what this property would characterize. Or they might want to test that D has what's called Hamming weight less than K. I don't know if you guys know what Hamming weight is, but the Hamming weight is basically the Hamming weight of a vector is basically the number of non-zero entries in the vector. Yeah, that's called a Hamming weight. It's a very famous notion. It's the number of non-zero vectors in the vector. Maybe they want to verify that the vector that the user sent them has at most k non-zero entries. Yeah, so these are things that we would like to test, and what I'm going to show you is basically how the servers can test for these 4 properties. That's my goal.
And in our
I think just a second, and this leads, I have to say, this leads to some very, very elegant algebra, which is what I wanted to show you today.
Yeah, and basically, like our specific example that we had before was that D is Boolean.
Yes, exactly. The example we had before was just a case 1, which is actually the thing that I'm going to talk about the least. So in fact, I'll just tell you, I'm not going to tell you how, but I'll just tell you that to prove that a vector is Boolean, the clients can actually send only log n elements. Yeah, so if the vector has length n, you only need to send log n elements, yeah, as a proof. And that already lets the servers verify very efficiently that the vector is Boolean. But I'm not going to show you how to do that. If you're interested in seeing how to do that, there's this paper that I linked here that shows how to do it. That's a little complicated. So I'll just tell you, it's kind of bizarre. It's kind of surprising that it's possible that just by sending log n elements, I can convince you that a vector is Boolean without revealing anything else about the vector. The things that I want to focus on today are basically the 3 other things. Yeah. So how do we prove that a vector is a unit vector? How do we prove that a vector has what's called norm k? So it's the sum of its element is at most k. And how do we prove that its Hamming weight is at most k? Yeah, these are the 3 things that I want to show you today. So are we clear on what we're trying to do? So the client is sending some vector over to these 2 servers. We want to prove the servers now want to check that the vector is one of these 3. Okay, that's our goal.
Yeah. Now, well, I have a question about the other thing with O log n. Why, if it sends O log n elements in F, why that still reveals some of the data?
No. Yeah. It turns out this is zero knowledge. It turns out these elements in the proof pi L and pi R, they are independent of the data. They're kind of not related to the data at all. I know it's surprising that this is possible, but again, if we're going to talk about zero knowledge, this is something that I'm going to have to come back and talk about because zero knowledge is a pretty big topic on its own right. Actually, Simon, I don't know. Was there ever a talk on zero knowledge at the Euler Circle or not?
Not in this class. I mean, when I teach cryptography classes, I teach about zero knowledge.
Oh, yeah. Okay. Yeah, so you guys should take the Simon's cryptography class and you get to learn more about how zero knowledge actually works. It's a very, very interesting topic, but that's not our goal for today. What I want to show you today is basically how can the servers test if a vector is one of these 3 things. Yeah. So they have shares of the vector. The 2 servers have, for example, 2 shares of D. The 2 shares sum up to D. And they want to test if the vector happens to be a unit vector, for example. Actually, let's start with that. So the key technique that we're going to use is actually something called sketching. Sketching is actually a classic technique from data structures. Here, we're going to use it for cryptography. So let me explain to you what sketching is. It's very, very simple. Yeah, very, very simple. You'll get it right away. And then we'll talk about how to build these sketches. So let's say that we have I'm going to use this funny script L. This is what's called something called a language. So we have a subset of vectors in F to the N, and those are the valid vectors. So for example, one example of a language L would be, the set of all unit vectors or the set of all binary vectors. Yeah, it's a set of valid vectors. Now, what's a sketch for the language L? So a sketch L with epsilon error is a pair. Yeah, there's an algorithm G and there's a polynomial F. So let me explain what this is. So the algorithm G is some randomized algorithm that basically samples a matrix Q. Okay, so this Q matrix, it's an M by N matrix. It's very, it's a rectangular matrix. It's a very shallow matrix where M is much, much, much smaller than N. Yeah, it's rectangular. And M in many of our examples is going to be 2 or 3. So it's like a 2 by N or a 3 by N matrix. Yeah. And F is going to be some M-varied polynomial, and it's going to have some low degree. It could be quadratic, cubic. It's going to have very, very low degree. And we'll see examples in just a minute. Now, what are the properties that G and F have to satisfy? The properties are, actually, you know what, before I tell you the properties, let me quickly say that this might look like a funny name, but in fact, if we take the matrix Q and we multiply by the vector D, you realize because the matrix is long and flat, Q times D is going to be much shallower, much shorter than the vector D, right? The vector D could have 1 billion elements in it, so N could be 1 billion, but when I compute Q times D, the resulting vector is only going to have M elements, like 2 or 3 elements in it. Yeah, so we took our huge vector D of 1 billion elements and compressed it into this thing called a sketch. And the sketch has length M, which, like I said, is going to be like length 2 or 3. So we did this major compression of the vector D using this matrix Q. And now what does it mean that the sketch is a valid sketch for the language? Well, we want to say that if D is in the language, then the polynomial F will always be 0 at D. Yeah, so if I apply F to the sketch, I'm going to get 0. And if D is not in a language, if I apply F to the sketch, the probability that I'll get 0 is very small. Okay, so again, this is kind of interesting that basically we took this long vector D, 1 billion elements, we squished it using this matrix Q into just 2 or 3 elements. Yeah, and then we apply this polynomial F, which is just a polynomial that takes 3, it's a 3-variate polynomial, for example. We apply this vector of length 3 to the polynomial F, and we either get 0 or not, and that will tell us whether the D is in the language or not. Yeah, it seems like impossible, right? Like, how can you take a vector D, squish it into so little information, and then have a polynomial F that tells you whether D was in the language or not based only on that squished information? And so indeed, the question is basically, which languages have a short sketch? Yeah, so a small m. That's our goal. I'm going to show you that the 3 examples I showed you actually have a short sketch, and that's going to be kind of, I don't know, it's pretty, I think it's very elegant constructions. It's good things for you to know, and it's actually very, very pretty math.
Hey, so
yes.
Just to clarify, an M-variate polynomial means like it takes an M inputs in some polynomial form.
No, it takes exactly. Well, okay. M-variate polynomial means it's a polynomial in the variables x1, x2, x3 up to xm. So it takes as input a vector of length m, which is exactly what we have, right? Q times D is a vector of length m. So we can feed that as input into F and then test if the result is 0 or not. Okay, great. So suppose we had such a sketch. How would we use it? Well, let me show you. So we want to test whether DL plus DR is in our language, right? That's what the servers want to do. So here's what they'll do. So jointly, they're going to generate this, they're going to run the algorithm G to generate this query matrix Q. Yeah, they're going to generate this M by N matrix Q. And now what's interesting, the sketch is a linear operation, which means that they can each locally compute their view of the sketch, right? So they can compute sort of the left side of the sketch and the right side of the sketch. And what we know is that if they add the left side to the right side, they'll actually get the true sketch S. Okay, so this is why this is such an important thing, because the data is split additively between the 2 servers, and that allows them to compute the sketch locally, to basically compute a sharing of the sketch locally, you know, a left side and a right side that happens to add to the actual sketch. And now it turns out, so this is our sketch, and now it turns out they have SL and SR, so SL plus SR is the real sketch. What they would like to do is test whether f of s is equal to 0, because that will tell them whether the data is valid or invalid. Okay. But they don't, S is not available to them, right? SL is available to one server and SR is available to the other server. And remember, they're not allowed to tell the data to one another because, well, that would violate the zero knowledge property. Yeah, because they want to keep the data hidden. But it turns out, again, this is a magical cryptographic tool, which I'm not going to be able to talk about today. Apologies, I need to rely on some background here. It turns out, if you have a low degree polynomial, for example, let's say you have a polynomial of degree 3 or 4. So T here is the degree of the polynomial of degree 3 or 4. It turns out there's a very efficient protocol between the two servers. So the two servers can talk to one another for T rounds for a degree T polynomial. And at the end, they will learn whether f of s is equal to 0, but they will learn nothing else about s. Yeah, so they just learn whether the sketch satisfies f of s is equal to 0, but they learn nothing else about the sketch. Yeah, so I know this is a little bit magical, but believe me, there's actually a way to do this that's actually quite practical. Okay, so once we have this, so what this shows us is that once we have a sketch, there's actually a very efficient way for the two servers to test where the data from the client is in the language or not. Yeah, I see that Sriram has a question. Sriram, go ahead.
So is this Q matrix generated randomly?
Yes, I'm going to show you exactly how. We're going to look through a bunch of examples. Okay, so let's walk through a couple of examples. And this is kind of where things get really interesting. Okay, so let's start with our first example. Our first example is we want to test whether the vector D happens to be a unit vector. Yeah, so it happens to be 0, 0, 0, 1, 0, 0, 0, for example. Yeah, so we want something that only accepts unit vectors. For a technical reason, I also need to accept a 0 vector, but that doesn't really matter. Okay, so how do we do it? So the query matrix Q is going to be built as follows. What they'll do is they'll choose random numbers R1 to Rn. Okay, so they choose random numbers. They choose a random vector that's as long as the data. R1 to Rn is as long as the data that we have, could be 1 billion elements. And they're going to construct a matrix which consists of two vectors, R, and a vector that I'll denote by R squared, which means basically take all the elements of R and square them. Okay, so our matrix, you see, it could be 1 billion long, but it only contains 2 rows in it. It's very, very shallow. And now the sketch, as a result, even though D might be 1 billion elements, the sketch Q times D is only going to contain 2 elements, S1 and S2. Let's be precise about what S1 and S2 are. S1 is going to be the inner product of the vector R with D, and S2 is going to be the inner product of the vector R squared with D, right? That's how matrix vector multiplication works. Okay, so now we have our query matrix, and there's a kind of a very cute theorem that we're going to prove in just a minute that says the following. If D actually happens to be a unit vector or 0, it so happens that the first element of the sketch, S1 squared, is equal to S2. However, if D is not a unit vector, the probability that S1 squared is equal to S2 is very small. It's just 2 divided by the size of our field. Remember, our field was quite large. Our field was like 2 to the 64. So the probability that we incorrectly decide that a non-unit vector is a unit vector is at most 2 over 2 to the 64. Yeah, and this is, again, the probability is over the choice of the vector R. All right, so let's just be precise here. What the sketch is actually using, you notice this test S1 squared equals S2 basically corresponds to the polynomial x squared minus y, because they're computing S1 squared minus S2 is equal to 0. That's what they're testing. S1 squared minus S2 is equal to 0, and it only has error 2 over f, which is actually very small error because f is very large. All right, so this sketch, this S1 and S2, actually let us easily test whether the vector is a unit vector or not. So let's see that. Oh, I see that Utsav has a question. Utsav, please go ahead.
Yeah, wait, so the QD is like S1 is R1 times R2 times R3 times R4 ...
No. When we multiply, this is a matrix vector product, right? So Q is the matrix here. Maybe I should have done this more graphically. Q is the matrix here. When we multiply by a column vector D, what are we actually doing? We're taking the inner product of the first row with our column vector, and we're taking, that's S1, and we're taking the inner product of the second row with our column vector.
Oh,
that's S2.
See.
Right, so S1 and S2 are these 2 inner products with the vector R and the vector R squared. Yeah, it's really kind of interesting. Again, we took this vector of size 1 billion, we squished it into only two elements, S1 and S2, and somehow this very simple condition lets us test whether the vector is a unit vector or not. Okay, so let's see, given that, let's see how the protocol actually works. So again, we have the two servers, they have DL and DR. We know the DL plus DR is the data. And we're trying to test if this data is a unit vector. So again, together, what they'll do is they'll generate this random vector R. Okay, now they will locally compute these inner products. Yeah, so they locally compute the matrix times the vector. So the inner product of D and R and D and R squared, D and R and D and R squared. Yeah, so they locally do this computation. And now they jointly want to decide whether the sketch, the first element of the sketch squared is equal to the second element of the sketch. Yeah, so they want to test whether this equality holds. And as I told you before, in fact, for this is such a simple test that for this, there's a very simple one round protocol that lets them test whether this equality holds without learning anything else about the data or the sketches or anything of that. Yeah, they only learn whether the equality holds and nothing else. Okay.
Also,
yeah.
And also, so this random R that we just generated here to do this computation has to be different from the one that splits D into DL and DR, right? Because then the
oh yes no
yeah.
very good catch. Yeah, this is I got a collision on my randomness. Yes, indeed. Yes, the secret sharing between DL and DR is an independent vector. This R is something that the servers choose themselves. Yeah, it's just very good memory. I use the same letter R, but it's actually these are unrelated vectors.
Yeah, they have to be, because
that's right.
Otherwise, well, one of them has the D minus the
right. That would
R,
be a problem.
and then yep.
Yeah, that would be a problem. Right. Very, very good point. So this is I should write this. This is a fresh random vector R1 to Rn, and that's what they do. Okay. So we have this theorem. So that's the protocol. I hope this is clear how the protocol works. Yeah, basically they each locally compute their share of the sketch. And then they run another protocol, which I'm not going to tell you about today, which tests whether the polynomial x squared minus y happens to be 0 on that sketch. And it does it in zero knowledge without revealing anything other than whether the equality holds or not. Okay, so we have this Q theorem. Let's go ahead and prove it. Oh, why is my thing stuck? Here we go. So we have this Q theorem. Let's go ahead and prove it. So what was the theorem? Let's look at this again. So the theorem said if D is a unit vector, then in fact, D inner product R squared is equal to D inner product R squared. Otherwise, if D is not a unit vector, this probability is very small. So here's a puzzle for you guys, just to see if you guys are following. I wonder if anybody can prove part one. Part one is quite easy to prove. And I'm wondering if anybody can tell me why that's true. Yeah, if not, I'll show you. Yeah, remember a unit vector means that the vector only has one position is equal to 1 and all the other positions are equal to 0. So what can you tell me as a result about the inner product of D and R?
It's just one of the components of the vector.
Perfect. Excellent. So indeed, if D is a unit vector, let's say it's position I, it happens to have a 1. Well, what do we know about the inner product of D and R? Well, the inner product of D and R is the sum of Di, Ri, but all the Ds are 0. So most of the sum is just zeros. Yeah, except one of the Ds happens to be equal to 1. And so what we'll get is Ri squared. Yeah, Di happens to be equal to 1. So we'll get Ri squared. This was supposed to be sum of Dj, Rj. Okay, so we get Ri squared. On the other hand, on the other side, we get the same thing. D inner product R squared, yeah, is simply, again, the entire sum disappears. The only term in the sum that survives is the term Ri squared. So indeed, they are equal to one another. So part one is kind of immediate. Yeah, part one is quite simple. Part two is Vedant, you have a question. Please go ahead.
Oh yeah, I was just wondering, so how many parameters typically will the vector D have?
Yeah, D could be as long as we want. D could be 1 billion elements. Yeah, so the client might actually have a lot of data that it wants to send to the server. Doesn't matter how big it is.
Okay, I understand.
Yeah, it's quite interesting. Yeah. Right. Okay, so part one is actually quite easy. Part two is the more interesting one, The reason part 2 is important is because we want to say that if D is not a unit vector, then the servers will reject that D. Yeah, so this equality will hold with very low probability, so the servers will reject it with very high probability. Okay, and so let's see why that's true. So suppose,
sorry, excuse me. Generally, like, what's the value, or like, what's the cardinality of the field that you use?
yeah, so we said at the beginning, the field is like 2 to the 64. So
Oh,
2 to the 64 is a pretty big number.
Yeah. Okay.
But
So
mine is
two-
59, so it's prime.
It's around 2 to the 64 minus 59. Yeah, exactly. So 2 divided by 2 to the 64 is small enough that the servers are not going to get fooled. Yeah, that's kind of the point. Great. Okay, let's go and prove part 2. So part 2, basically, to prove it, we have to say, suppose D is not a unit vector. So what does it mean that D is not a unit vector, N is not 0? Well, to keep it simple, let's just say D has at least two non-zero entries. That's the interesting case. Yeah. Yeah, it's not a unit vector, which means it has at least two non-zero entries. Remember, I told you that a unit vector means you can only vote for one thing. Well, here the client is trying to cheat, and is trying to vote for two or more things. So we'd like to basically ignore that contribution from that client. Well, so the question is, how many random vectors are there that satisfy this equation? Yeah, dr squared is equal to dr squared. Those are the bad r's. Yeah, we'd like to argue that there are very few bad r's. How do we do that? Well, we're going to go and treat this equation as a polynomial equation, right? We can replace r by variables in a polynomial. Yeah, so x is going to be our vector of variables, x1 to xn. And we're asking basically how many solutions are there to this n-variate polynomial equation, right? This is a polynomial equation in n variables, x1 to xn. And we're asking how many solutions are there to this polynomial equation. Every such solution will give us a bad r. So we want to argue that there are very few solutions to this one polynomial equation. So how do we argue such a thing? How do we argue that there's very few solutions to a polynomial equation, to a multivariate polynomial equation? Well, for that, there's actually a very, very general tool. This is a lemma that you guys need to know because it's actually a pretty important lemma. It comes up all over the place in cryptography and in computer science in general. It's called the Schwarz-Zippel lemma. Yeah, so the Schwarz-Zippel lemma says the following. Suppose G is a non-zero n-variate polynomial. Yes, it's a polynomial in the variables x1 to xn. Yeah, and it has total degree t. Okay, so what's the total degree? Total degree is basically the sum of all the degrees. So for example, this monomial here, x1 squared, x2 cubed, has total degree 5 because we sum the degrees of the different variables. Okay, then it turns out you can prove the numbers of zeros of G in f to the n is bounded by this expression here, t times f to the n minus 1. Just as a sanity check, can somebody tell me what happens when if we apply this lemma to a univariate polynomial? Suppose we apply this lemma in the case n is equal to 1. What results do we get? Yeah, if n is equal to 1.
Fundamental theorem of algebra.
Fantastic. You guys are perfect. That's exactly right. If n is equal to 1, this is a univariate polynomial. Yeah. So what the lemma would say is that the number of zeros of a univariate polynomial in a finite field is at most the degree of the polynomial, t, which is exactly, it's not exactly the fundamental theorem of algebra applies over the complexes, but it's the same, it's basically the same thing, just over a finite field. Yeah.
And to be clear, the total degree is not like you take all the terms and all the exponents and you add it up. You take, so you have a total degree of one term, and then you have a total degree of one term, and then you take the maximum of all the total degrees of each of the terms.
Exactly.
And that's
exactly. That's the total degree.
Would
Exactly.
like a univariate polynomial only have like 1 0 or like 0 0 because it's a line?
I'm sorry, say that again.
Would a univariate polynomial only have 1 0 at most because it's just a line?
No, a univariate can have degree 5, can have degree 100, right? X to the 100 plus x to the 99 plus x to the 98 plus 1. That's a univariate polynomial of degree 100. That's not a line.
Oh, I see.
Univariate means it only has one variable, x. Yeah, it's not linear. What you're asking is about a linear polynomial. Yeah. Okay, terrific. By the way, I would encourage you to try to prove this lemma yourself. It's actually not that hard. Yeah, this is a very cute proof. You guys already told me that it's true when n is equal to 1. The rest is just a proof by induction. Yeah. Now assume that it's true for n and try to prove it for n plus 1. It's not a totally immediate proof, but it's not that hard either. So I would actually encourage you to try to prove this lemma by yourself, because it's actually a very important lemma. Okay, so how does it apply in our case? Well, suppose that D has at least 2 non-zero entries. Remember, we were interested in this polynomial. The question was, how many zeros does this polynomial have in f to the n? Well, so the first question we have to ask is this the zero polynomial? Can D have at least 2 non-zero entries, and this will be the zero polynomial? I claim that no, it cannot be the zero polynomial. And can somebody tell me why? If D has 2 non-zero entries, why can this not be the zero polynomial? Let's see if you guys can tell me why. By the way, I should say, if D only has 1 non-zero entry, sorry, if D is a unit vector, if D is a unit vector, this polynomial actually is the zero polynomial. It takes a minute to convince yourself, but for unit vectors, when D is a unit vector, this is a zero polynomial. The question is, when D has 2 non-zero entries, let's say that the first and second entries of D are non-zero, so D1 and D2, they're non-zero. Why does this imply that this is a non-zero polynomial? Let's see if somebody can tell me.
It's like there's like
the
a
first term you get like x1 plus x2.
Wait, one at a time. One at a time. Somebody who's not so hum.
Oh yeah, sorry. But for the first term, you get like dixi plus or d1 x1 plus d2 x2 whole square.
Yes.
And then that's like different from the second term, which is like d1 x1 square plus d2 x2 square. You have like the extra term of
yes, that's exactly right. Actually, when you expand the quadratic, you'll get x1 times x2 on the left, but there's no x1 times x2 on the right. Right? All the terms on the right, they're kind of pure monomials. Yeah, so x1, x2 on the left cannot cancel with anything on the right. Yeah, so therefore, this cannot be the zero polynomial. Yeah, good, excellent. You got it. You guys got it. Well, if it's not the zero polynomial, the lemma tells us that there are at most, right? Its total degree is 2. So there are at most 2. There are at most 2 times f to the n minus 1 solutions. Each solution corresponds to 1 bad r. Yeah, but that's great because the probability that we chose a bad r is the number of zeros, 2 to f to the n minus 1, divided by the total number of r's, which is f to the n, which is 2 to the f, which is exactly what we wanted to prove. You see, so the probability of the servers if the client is trying to cheat and D is not a unit vector, the probability that the servers will choose a bad R is very small, and as a result, the client will have its data rejected because the equality is not going to be satisfied.
So I have a question.
Yeah.
So first of all, this situation seems a bit weird. Like, so basically the client is trying to compute the sum of all
the server is trying to compute the sum of the vectors from the clients.
Well, I mean, it's what the client wants. The sum is what the client wants, and the server doesn't want it. It's just helping the client. And
no, the client is the phone. When I say client, I mean phone here, right? The phone is sending this vector D, and the two servers are trying to convince themselves that the vector D is a unit vector.
Yeah, but also, but is the client the one who wants them to do it?
No, the servers are trying to compute this. The servers are trying to compute the sum of the vectors from the clients.
Oh, because the servers want to know.
That's right. So the servers here want to check that the client is sending them unit vectors. They can't, the app server can't do it by itself because it only sees one share. But together, the two of them can test that the vector is a unit vector without learning anything else about what the vector is.
And they also do the whole summation process that we mentioned earlier in the case of the Boolean vector.
That's right. That's right. Yeah.
Mhm.
Here we're talking about a different case. We're talking about
They
the,
want to do it, not the client.
that's right. The servers want to compute the sum. Yep. Okay, good.
Mm,
Client.
So we have a,
why is it at most 2f to the n minus 1 bad randoms?
well, what's the, look at this. Let's look at this polynomial G. What's the total degree of G? Yeah, the total degree of G is 2. Yeah, because you can see that every monomial has degree at exactly 2. Yeah, so the total degree of G is 2. And so the theorem would tell us that the number of zeros is 2 times f to the n minus 1,
I see.
right? And so there are at most 2 times f to the n minus 1 bad vectors R. And that's great because there are a total of f to the n vectors overall. So therefore, the probability of choosing a bad vector is very, very small. Yeah, does that argument make sense?
Mm-hmm.
No, please ask. If something is not clear, please ask. I want to make sure this is clear.
I don't think I'd be 30, right?
Sorry, you were breaking up. You were saying what?
I think it makes sense based on the theorem you gave, yeah.
Okay, great. Yeah, and this theorem, like I said, it's kind of a fun theorem to try to prove yourself. You basically would prove it by induction on the number of variables, induction on n. Okay, let's do another example. Actually, how are we doing on time, Simon? Should I stop or should I do one more example? Because the second example is kind of cute.
Yeah, go ahead.
Okay, let's do, well, maybe we'll run 10 minutes late. But the second example is kind of cute. So the second example. Sorry, what?
Also, I have another thing. So basically, so in one case, we're trying to show that the client is not malicious by showing the client has real data. And we're also, in the other case, we're showing that the servers aren't malicious because we're making sure they don't find out more.
That's right.
Yeah.
That's right. We have a lot of constraints to satisfy here. The client have to send a valid data, and the servers are not allowed to learn this data in the clear. They only need to learn the sum. Yeah, exactly. Okay, let's do another example. So the second example is actually very cute. So I'm going to generalize. It's a generalization of the first example. So we're going to define this language LK, which is exactly the case that we talked about, where you are not just supposed to vote for one element. For one restaurant, you can vote for up to k restaurants. Yeah, so we want the vector to be d1 to dn. Each element di is some number between 1 and k, and the sum of all the di's should be less than k. This means basically you can vote for at most k restaurants. Again, think of k is equal to 5 or 3. Let's say it's 3. So you can vote for at most 3 restaurants, and it's fine to vote for the same restaurant more than once. Okay, so the servers are trying to convince themselves that the vector from the client is in this language LK. Yeah, and I wrote down some examples in the language L3. What we're going to do is we're going to build a sketch of size k plus 1 for LK. Yeah, so the sketch is still going to be very short. For example, for L3, the sketch will be of size 4. Okay, so how does a sketch look? So again, they're going to choose random elements, a random vector R1 to Rn. This time, they're going to build a slightly more complicated query matrix. So I wrote down what the query matrix is right here. You can see the sketch now is going to have k plus 1 terms in it. Yeah, because this matrix has k plus 1 rows. Therefore, the sketch is going to have k plus 1 elements in it. Again, think of k is equal to 3. So we took our huge vector of size 1 billion. We compressed it to 4 elements. And now the question is, how do we decide if the vector d is in LK just given the sketch q times d? That's what the parties actually needed. All they have is a sketch, and they want to decide whether the vector belongs to LK. So how do we do this? And here, there's a kind of a cute tool that we end up using. We end up using what's called the Newton identities. So Simon, here, let me ask: did you cover the Newton identities in the class or not?
They've probably shown up in some classes, but not in this class. So in this class, all the students have their own projects. So some of them have seen it in the context of their projects, but it's not.
Got it. Okay, let me quickly remind you what the Newton identities say. So it's very simple. So basically, we're going to define polynomials. So we'll define the power sum polynomial, which is basically, p sub t is the sum of tth powers of x1 to xn. Okay, and I wrote down some examples of what p1, p2, p3. I just wrote them down over here. And we're going to define the symmetric polynomial. Sometimes this is called the elementary symmetric polynomial as the sum of here. This is a little bit harder to explain. It's kind of the sum of all t-wise choices of the variables. So for example, E1 would be just a sum of x1, x2, x3. E2 would be the sum of all pairs. E3 would be the sum of all triples. Well, there's only one triple, so E3 is very simple. Yeah. And so this is called the symmetric polynomial. Yeah. So there's these two families of polynomials, the power sum polynomials and the symmetric polynomials. This, by the way, this continues to E4, E5, E6, P4, P5, P6. And what Newton discovered is there's a very cool relation, very simple relation between these polynomials. And it turns out that's exactly what we need here. Yeah. So I'm going to say Newton's identities actually in a kind of an unusual way, but that's what we need. So it turns out that, in fact, for every t, there's a certain polynomial, which I'll denote by n sub t. It's a polynomial in t variables, which oddly, if I evaluate, if I have already computed the power sum polynomials, P1, P2 up to Pt, yes, so I already computed my power sum polynomials. If I plug those sums into nt, I actually get the symmetric polynomial. Yeah, so basically what this says is if I want to compute E2, I can easily compute E2 from P1 and P2. Yeah, there's a simple polynomial that combines P1 and P2 and gives me E2. Similarly, there's a simple polynomial that combines P1, P2, and P3 and gives me E3. That's what Newton noticed. And in fact, this polynomial nt satisfies a very simple recurrence. I even wrote down the recurrence here. You see n sub t is defined in terms of n sub 1 up to n sub t minus 1. Okay? And so there's a very simple recurrence to compute these nts, and I even wrote down some examples for you. So n1 is very simple, n2 happens to be just that, n3 happens to be that, and so on and so forth. Yeah, so if I compute the first three power sum polynomials, I can compute the symmetric polynomial, the third symmetric polynomial from those three values. Okay.
And I can see a factorial forming there too.
You can see what?
A factorial forming there too. There's like
yeah, that's right. That's right. In fact, there is a factorial. That's not a coincidence. There is a factorial there.
Mhm.
Indeed. Okay. So for our sketch, remember we had our funny sketch here, which is Q and Q times D. It turns out D is in the language LK. Remember, this is the language of where you can vote up to K times, at most K times. It turns out if D is a valid vector in the language, then when I evaluate this polynomial nk plus 1 on the sketch Q times D, I get 0. You notice I get K plus 1 terms here. If I plug these K plus 1 terms into the Newton identities, I get 0. Okay. However, if D is not in the language LK, then it turns out that you'll get 0 with very low probability. It's K plus 1 over F. You know, if K is 5, 5 over F is still or 6 over F is still very small. Yeah. So again, we have a sketch that that tells us exactly whether an element is in the language or not, directly using these Newton identities. And again, this leads to a very simple protocol. Basically, they'll generate random R1 to Rn. They'll compute the left side of the sketch and the right side of the sketch. And now they just have to evaluate this polynomial nk plus 1 and test whether that's equal to 0. And this, again, can be done using a simple protocol that takes k plus 1 rounds between the servers. Yeah, very, very simple protocol that lets them compute this value without learning anything else about SL or SR. Yeah, so again, we can test. They can very easily test by themselves whether the vector is a valid vector or not. Okay, cool. I think I'm going to stop here. Actually, the third example was going to be about the Hamming weight example. Maybe I'll just leave it for you as a puzzle. I'll tell you, so here the question is, can the servers convince themselves that the vector from the client contains at most W non-zero elements? And I'll tell you that there's a very cute sketch for this language of size 2W plus 1. Yeah, so you can just compress this huge vector into 2W plus 1 elements, and that will let you test whether the vector is an LW or not. So maybe this is a good puzzle for you to think about. If you give up, you can look. This is in our paper that shows how to do it. So yeah, so maybe I'll stop here. was going to give you some hints, but maybe I'll stop here and tell you, just to summarize, basically what I showed you is that we can efficiently compute statistics over private data without leaking anything else about the data, like summations, for example, over private data, without leaking anything about the data other than the sum. It can be made robust against misbehaving clients. Sometimes we need to include proofs. Sometimes we can verify properties directly using sketches. And as we said, the helper server is only there to make sure that the central server is not asking for queries over sets that are too small. That's in some sense the only purpose of the helper server. Yeah, and I'll tell you that this system is actually now being used. Surprisingly, yeah, there are a couple of companies that already deployed this so they can collect information about their user base without actually learning anything about what their users are doing. All they're getting is like aggregate information about their user base, but they see nothing about user data. So it's very cute that all this beautiful math that comes up here is actually used to provide privacy for user data. Anyhow, so that's what I wanted to show you today. Yeah, I hope you you got something out of this. I hope you enjoyed it. You have some puzzles to think about, and yeah, hopefully you learn more about this area.
Thanks. So are there any questions?
So this is a pretty new discovery because you said that some companies are already using this. Is this something that's been discovered new or for a long time?
Yeah, this is very recent. So what's mostly used by companies, oddly, is the binary results. The other examples I showed you today, they're very, very recent. Where is this? So yeah, so the Boolean case is what's actually mostly being used by companies. The examples I showed you today, they're more recent, and hopefully they'll be used too.
Wait, could you show the link to the paper again?
Here, it's right here.
Okay, yeah, thank you.
Yeah, this is the binary case. Yeah, cool, great. Any more questions?
Could you talk a bit on why that the modulo number has to be prime in order for it to not be?
Oh, yeah, good. Okay, why do we need a prime number? Well, let me tell you this. So it all comes back to the Schwarz-Zippel lemma. So the Schwarz-Zippel lemma was pretty crucial for everything that we did. In fact, even for the later theorem, the Schwarz-Zippel lemma is very important. And remember when we plugged in n equals 1, we got the result that says that G has at most T roots. If G has degree T, it has at most T roots in F. It turns out that's only true. So you guys told me that's the fundamental theorem of algebra, right? That a polynomial of degree T can have at most T roots. Well, that's true when you work modulo a prime. It turns out when you work modulo a composite, that's actually not true. Yeah, it's kind of interesting that when you work modulo a composite, a polynomial of degree D can have many, many more roots than just D. Yeah.
Yeah, it's this argument about how it's not really a field when it's modulo composite.
That's
now
right.
I see, because I thought we were just doing addition, addition as modular arithmetic earlier, and it's not multiplication, but polynomials involve multiplication. So I see
That's
now.
right. That's right.
Yeah.
Yeah. So actually, if you work modulo a product of two primes, then by the Chinese remainder theorem, basically a polynomial of degree T can have up to T squared roots. Yeah, it's kind of weird. Polynomial of degree T modulo composites can have modulo products of two primes can have T squared roots, not T.
What
But
is
over-
modulo prime plus modulo composite?
I'm sorry, what? Can you say that again?
What do you think modulo prime plus modulo composite? But how do you do modulo off a polynomial, not just a number?
How do you do modulo? Well, here we're just talking about modulo numbers, right? Modulo a prime or modulo a product of two primes, for example.
How would a polynomial be taking the modulo off?
Well, if I give you a polynomial of degree T, and I ask you, how many roots does it have modulo 15? Well, that would just be looking at the numbers 0 to 14 and seeing how many of them happen to be 0 of this polynomial modulo 15.
I see.
Yeah. And I'm saying that modulo 15, a polynomial of degree 3 could actually have many more than 3 roots. Yeah, maybe you guys can even think of such a polynomial. But modulo 17, a polynomial of degree 3 can only have 3 roots. Yeah, that's the benefit of working modulo a prime. That's why we like working modulo primes. Yeah, so the Schwarzschild lemma only holds modulo primes. So it has to be a field, otherwise it's incorrect. Yeah, it's a good question. I'm glad you asked that. Yeah, great. So I think I kept you actually longer than I promised. And so, Simon, is this a good place to end?
Yep, sure. So yeah, thanks for a great talk.
Yeah, terrific. Okay, I hope you enjoyed it. And good luck with, you guys are very lucky to have Simon as your instructor. It's Simon, thank you so much for running the Euler Circle. Yeah, enjoy the rest of your course.
Okay.
Thank you.